In this video, we'll talk about solving logarithmic equations in kind of an introductory capacity. This will be an introduction to a series. There will be a couple more parts of how to solve logarithmic equations. So let's go ahead and just kind of start with an example. So a lot of what we're doing here with these logarithmic equations is we're looking at how to solve a logarithmic equation without the use of the change of base formula or a lot of the properties of logarithms that we have available to us. So we kind of have some of our, or at least one hand tied behind our backs here. But that's okay. We're just going to look at this on more of a conceptual level, as these thoughts will be motivated later to help us solve more advanced logarithmic equations. So let's go ahead and take a look. We have log base 3 of x equals 4. Now if we're looking at this, we don't have a lot of knowledge of what a logarithm is or how to solve it at this point because we don't have a lot of the tools available to us yet. That's okay. One tool we do have, though, is we can turn this into an exponential equation. And keep in mind, there's an example I use to kind of help myself keep it straight. 2 cubed equals 8 if and only if log base 2 of 8 equals 3. These two equations have the same meaning. We're just rewriting it as an exponential or a logarithm instead of what we have. So right now we have a logarithm and we want to write it as an exponential to kind of maybe see if there's a chance that we can solve that equation easier. Because if we can solve one of them easier, great. So let's go ahead and do it. 3 is our base. So we have 3 to the power of 4 is equal to x. Now this equation, much easier to solve than this one. I can take 3 to the 4th power, that's 81. So x equals 81, I'm done here. There's my solution. Now something that's worth noting, and it's not really a problem on this one, you'll want to double check to make sure your solutions work with logarithms. Say I have a negative. I don't know how to take a logarithm of a negative number. Log base 3 of, say, negative 81 is undefined. So if that was the case where I worked it out and the only solution I had was x equals negative 81, then I would write there's no real solution. So just keep that in mind. Whatever we plug into a logarithm has to result in a positive number. It can't even be 0, because 0 or less is undefined for a logarithm. So just keep that in mind. It's worth noting sometimes it does happen. You do get those extraneous solutions. So let's talk about a slightly different example. Let's say I have logarithms on both sides of the equation. Well, kind of similar to when we talked about this with exponentials. Say we had 2 to the 5th equals 2 to the x. Well, then this could only be true if x equals 5. Basically, these powers have to be equal. Very similar thought here. We have log base 7 of some stuff equals log base 7 of some other stuff. So I have the same function, I have different inputs, and I know the outputs are equal. Well, the only way that can be true is if these two green expressions I've underlined are indeed equal. So I can, in essence, drop the logarithms. Now that only works if I have same base and a single logarithm on either side. If I had log base 7 of x minus 1 equals log base 7 of 2x plus log base 7 of 8, I could not do this trick. It has to be a single logarithm and it has to have the same base. But since that is the case here, we can say x minus 1 has to equal 2x minus 8, which I can now solve this equation much easier. This is a linear equation. So I'm going to go ahead and subtract x from both sides, and then I'm going to add 8 to both sides. So x equals 7. Now again, I'm just going to plug it in and make sure it works. So I have 7 minus 1, which is 6. I can take log base 7 of a positive 6. That's fine. So that works. And then likewise, I'm going to plug it in over here. 2 times 7 makes 14 plus 8 makes 22. And we can take log base 7 of a positive number. Now, something that is a little interesting here is that you have log base 7 of 6 is equal to log base 7 of 22. Now, we don't necessarily have the capabilities yet to assess this, but there's no way this can be true. This would be like saying, oh, y equals, or 2 to the 4th power equals 3 to the 3rd power. It's just not possible. So in this case, technically, there would be no solution. So this would be an extraneous solution. It's just worth mentioning here. It can happen, so be careful. But the thought still applies. If I have a single logarithm equals another single logarithm, I can set essentially the guts of the logarithm equal to each other. I can drop the logarithms in a manner of speaking. And these equations do get more complicated. We will develop some more tools to solve them. And once you've kind of developed those tools, that makes the process a little easier. But the whole idea of converting between a logarithm and exponential or condensing to single logarithms is very, very much applicable even in those more complex equations. So this is a very general thought, but it carries through to any future solving of logarithmic equations. So just keep this in mind. This is a good reference to just kind of help guide the thinking.